The goal of this lecture is to show you the pushdown automata define exactly the context-free languages. So let's get to it. Besides the comfort of knowing that two seemingly unrelated concepts are really the same, the grammar PDA equivalence will let us jump between the two notations when we talk about properties of context-free languages. The ability to jump between different representations, regular expressions and deterministic finite automata, was important when we addressed properties of regular languages. And we shall find the ability essential for context-free languages as well. We also find it easier sometimes to describe a PDA for a language rather than a grammar. For example, you might find it hard to invent a grammar for balanced parentheses, but a PDA is easy to think of. Just push left parens onto the stack and pop the stack once every time you see a right parenthesis. If the bottom of stack marker is exposed, then the parentheses were balanced, and you never pop the bottom marker because that would mean you have more right parens than left. Let's start with a language L that has a context-free grammar G. We'll convert grammar G to a PDA P that accepts L by empty stack, and if you want a PDA that accepts L by final state, we know how to convert to one of those. P will have only one state Q, that's all we need. Naturally, Q is the start state. There are no final states because we are accepting by empty stack. The input symbols of P are the terminals of G. The stack symbols of P are all the terms and variables of G. And the start symbol of P is the start symbol of G. Our intent is that P will step through a leftmost derivation of input W from the start symbol S. The secret is that each left sentential form is represented in a subtle way. It is whatever input P has so far consumed, followed by whatever is on P's stack. When P reaches an empty stack, then the left sentential form it represents is whatever input it has consumed, followed by nothing, that is, by the empty stack. That means P has found a leftmost derivation of the input string it has read, so acceptance of the string is justified. If no sequence of choices of the non-deterministic P leads to empty stack after consuming W from the input, then W is not a terminal string derived by the grammar, and P rightly does not accept W. There are two kinds of rules in the transition function of P, depending on whether a terminal or variable of G is at the top of P's stack. The type 1 rules handle the case where A is the terminal on top of P's stack. There better be an A as the next input symbol, or P has guessed wrongly about the leftmost derivation of the input as it actually exists. In effect, we cancel the A on the stack against the A on the input. The left sentential form represented does not change. We have now consumed one more input symbol A from the input, so that becomes part of the left sentential form. But the A that was at the stack top is removed, so it no longer participates in the left sentential form. The type 2 rules handle a variable, say A, on the top of the stack. We need to expand that variable by the body of one of its productions and thus move to the next left sentential form. Of course, we're only guessing. We have to allow any of A's productions to be used. If A goes to alpha is one of these productions, then a choice for P using epsilon input and with A on top of the stack is to replace A by alpha. We're going to prove that P accepts exactly what G generates. Formally, we will show something more general. It seems we always have to show something more general than what we really want. Here we show that if P consumes W from its input, starting with only S on its stack, and winds up with stack alpha, that is, this ID becomes that ID, okay, then in G there is a leftmost derivation of the string W alpha. Incidentally, notice that as we describe the moves of P, we allow any string X to follow W on the input. Since no part of X was consumed, X cannot have any effect on the moves P made reaching the ID shown. So if the statement is true for one X, it is true for any other. That is, X does not matter. We start with the only if part. That is, if P makes the transition shown, then S derives W alpha in G. The basis is 0 steps. Then W is obviously epsilon since nothing can have been consumed from the input. And alpha is S since the stack doesn't change. We need to show that S derives W alpha in a leftmost derivation. But W alpha is just S, and surely S derives itself. Now let's do the induction. We'll consider the result of n steps of P, that is, this ID has become that ID, and we'll assume the inductive hypothesis for sequences of n-1 steps. We must consider type 1 and type 2 moves as the last step separately. First, consider the case where the last of the n moves is a type 1 move, where an A at the top of the stack is cancelled against an A on the input. Then the W consumed by the n move sequence must be of the form YA. That's this. And before the last move, the Y was consumed. That is, leaving just AX. Further, just before the last step, the stack of P is A alpha. By the inductive hypothesis applied to the first n-1 moves, we can conclude that there is a leftmost derivation from S of YA alpha. That's this, and it corresponds to the fact that there is an n-1 step derivation of that ID. But YA is W, so we already know that there is a leftmost derivation of W alpha. That is the needed conclusion for the full sequence of n steps. Now let's look at the case of a type 2 rule, where there is a variable A on the top of the stack after the n-1st move. After n-1 moves, P has consumed W from the input and has A beta on its stack. That's that. This, of course, is the ID after n-1 moves. At the nth move, no input is consumed, but A is replaced by gamma, one of its production bodies. Okay. That is, we assume A goes to gamma is a production. Okay. Notice that alpha is gamma beta here. That is, this stack string is really alpha. Okay. Again, we apply the inductive hypothesis to the first n-1 steps. We thus know that there is leftmost derivation from S of WA beta. Since A is clearly the leftmost variable, and A goes to gamma as a production, there is also a leftmost derivation of W gamma beta. That's that. And of course, gamma beta is alpha, so that is really a derivation of W alpha, as we wanted to prove. We also should prove the converse, but we won't. That is, we need to show that if there's a leftmost derivation of W alpha, that is this, then P can consume W from its input with any unseen X following, and turn stack S into stack alpha. The proof is an induction on the number of steps of the derivation, but that's as far as we will take it. Assuming we complete the proof of the converse, we have the statement we set out to prove. P can consume W from its input with any X following, and turn stack S into stack alpha, if and only if G has a leftmost derivation of W alpha. Now we can restrict the statement to what we really care about, the case where X is empty, that is, P has consumed all its input, and alpha is also empty, that is, P has emptied its stack and accepted. We conclude that P consumes W while emptying its stack if and only if there is a leftmost derivation of W in G. That is, W is in N of P if and only if W is in L of G. For our next trick, we'll show how to convert PDAs to grammars. Assume language L is accepted by PDA P by empty stack. If it were accepted by a final state, we already know how to construct a new PDA that accepts L by empty stack, so we're entitled to assume acceptances by empty stack. We'll construct G, a grammar for L, and the idea is to give G variables, which we'll denote by PXQ with brackets around them, like this. The job of this variable is to generate all and only the strings W, such that while reading W from the input, P goes from state P to state Q and appears to pop X from the input. While doing so, P can grow the stack well above where X was, but it can never go below where X was, and at the end the stack is shorter by 1 than it was when it started. That is, the net effect is that X has been popped. Here's a picture showing the height of the stack while X is effectively popped while reading W. Note that X might be replaced at the first move or later by another symbol Y. It could even be replaced many times, but the position of the stack that originally held X is never popped until the last move, right at the end here. As we mentioned, for every pair of states P and Q and stack symbol X, there is a variable that we represent by the composite symbol PXQ. Although this expression consists of 5 characters, you must think of it as a single symbol in the set of variables of G. Also, as we hinted, the job of PXQ is to generate all strings W that have the effect of taking PDA P in state P with only X on the stack to the ID where the state is Q, the input has been consumed, and X was popped. That's that. Notice that since the initial ID shows nothing below X on the stack, we know that X can't be popped until the last step, since PDA P cannot make any moves when its stack is empty. And there is one more variable of G, the start symbol X. There may be many productions for variable PXQ. For each move of the PDA from state P with X as the top of the stack, we produce one or more productions. There are several cases, and they get increasingly more complex depending on how long the stack string is that replaces X at the first move. The easiest case is that of a rule that says in state P with input A, which could be epsilon or a real symbol, we pop X. That's that. Okay. There, X is replaced by 0 symbols. Then there is a production PXQ goes to A. The reason this is correct is that reading only A is one way to have the net effect of popping X while going from state P to state Q. The next simplest case is when a move replaces X by a string of length 1, say Y. Suppose that move also changes the state to R. Then there is a production PXQ goes to A RYQ. That is, one way to pop X while going from state P to state Q is to read input A, going to state R and replacing the X by Y at the top of the stack. Then some number of inputs, say W, has the net effect of popping the Y while going from state R to Q. As a consequence, the net effect of reading A followed by W is to take state P to state Q while popping the original X. Here's a picture of the case where X is replaced by a single symbol Y. How the Y gets popped we don't know, but when it does, the effect is that the symbol A followed by whatever W popped the Y has the effect of popping X while going from state P to state Q. Now it's getting a little more complicated. Suppose there is a move that replaces X by 2 symbols, Y and Z, while going to state R and reading A from the input. That is, the new stack YZ replacing X. In order for X to be erased, there must be some input string U that has the net effect of erasing Y, and U must take the PDA from state R to some state S, which unfortunately we don't know. As a result, we're going to have one production for each possible state S. But after reaching state S, we must have some additional input V that takes the PDA from state S to state Q while popping the Z from the stack. The net effect is that A followed by U and then V pops X from the stack while going from state P to Q. Okay. Here's a picture of that action. Initially you see X got replaced by Y and Z on the stack. Then U had the net effect of replacing Y, of popping Y, exposing the Z. Now we're in state S. And then V has the net effect of popping the Z and winding up in state Q. So we generate many productions for this case, where on input A, state P becomes R and X gets replaced by the stack, on the stack by Y and Z. For every state S, there's a production with head PXQ, and then the A that causes the first move. Remember, A could be empty. And then RYS to effectively pop the Y, winding up in this state S that we really don't know, so that's why there's one production for each S. And then SZQ to effectively pop the Z. We finally wind up in state Q, which is the state that we wanted to wind up because that's the state that appears in the head. As a result of this production, you can see that PXQ can derive any string AUV provided that RYS derives the U and SZQ derives the V. In the general case, where on input A in state P, X is replaced by a string of 3 or more stack symbols, Y1 through YK, and the state becomes R. We need a family of productions in which there are k-1 unknown states, S1 through Sk-1. Right. The productions all have this form. PXQ can be replaced by an A, which again may be epsilon, followed by variables R, Y1, S1, S1, Y2, S2, and so on, with the last of the variables being Sk-1, Yk, and finally the state Q from the head that we want to wind up in. With productions constructed in this manner, we can prove that P accepts W by empty stack. That is, the ID Q0 W Z0 goes to P epsilon epsilon if and only if the variable Q0 Z0P derives W. We're not going to give the proof. It is 2 easy inductions, one for each direction. The only problem is that we don't know state P. But remember, G has another variable S, and that is the start symbol. So we add production S goes to Q0 Z0P for every state P. And now we have a grammar that generates exactly the strings that the PDAP accepts.